Okay, hello. So for this video, we will be discussing elimination of arbitrary constants. So elimination of arbitrary constants is a way for us to verify if we have obtained the correct solution of a differential equation. So as we have discussed earlier, uh, when solving differential equations, in finding the solution of differential equations, so we obtain arbitrary constants in the solution. Okay, and the number of the arbitrary constant depends upon the uh, highest order of the derivative appearing in the original differential equation. Okay, so this is a way to again verify if you have if you have arrived to the correct solution of the differential equation. So by elimination of arbitrary constants, so the solution of the differential equation must go back to the differential equation. So this is quite simple and straightforward. So all you need to do is your knowledge. All you need is your knowledge in algebra and differential calculus. So in eliminating arbitrary constants, so the number of arbitrary constants is also the number of times you have to derive the function to eliminate the constants. Okay, so since we have C1 and C2 in our example, so find the differential equation whose general solution is y is equal to C1 e to the negative 2x plus C2 e to the x. So we have two arbitrary constants. So therefore, we need to derive the equation twice. Okay, so solution. So we need the first and the second derivatives. So again, our given is y is equal to C1 e to the negative 2x plus C2 e to the e to the 3x. Okay, so we need the first derivative, y prime. So y prime is equal to, we have a numerical coefficient, so write that and then derive this. So the derivative of e raised to negative 2x, so recall that the derivative of e to the u is equal to e to the u plus du over dx. So therefore, just write the exponential function e to the negative 2x and then multiply it by the derivative of its exponent. So the derivative of negative 2x is negative 2. Okay, so the same with the second term. So c2 is a constant, so write that c2, same exponential function, so rewrite e to the 3x and then multiply it by the derivative of the exponent. So derivative of 3x with respect to x is 3. Okay, so therefore simplifying, our first derivative is equal to negative 2 c1 e raised to the negative 2x plus we have 3 c2 e to the 3x. Okay, so let's name that as our equation 1. Okay, so next is get the second derivative. So again, we need to derive this twice, okay, because we have two arbitrary constants. So for the second derivative, so deriving this again, so negative 2c1 is a constant coefficient, so write that 2c1 and then multiply again by the derivative of e raised to the negative 2x. So the same with what we did for the first derivative, so write e raised to the negative 2x times negative 2 and then plus, so 3c2 and then the derivative of e raised to 3x is e raised to 3x times 3. Okay, so our Our second derivative, therefore, y double prime is equal to positive 4 c1 e raised to the negative 2x plus 9 c2 e to the power of 3x. So name that as our equation 2. Okay, so to eliminate the coefficients, we will be using these three equations. So we have started the first derivative as our equation 1, second derivative as our equation 2. So actually we also need the original function. So you can just name this equation 3. Okay. So but this should have been the equation 1 originally. Okay. So first is we will be using equations 3 and 1, okay, to eliminate c1 or c2. So it depends. So this will work like elimination. If you recall the elimination method in solving for simultaneous linear equations, okay, so that would be similar to this, analogous to this solution. So one by one, so we will eliminate either C1 or C2. So it's up to us to decide what variable would we eliminate first. Okay, so if you want to start with C1, eliminating C1, then you can do that. So eliminate C1 from equation 1 and equation 3 and equation 1, and then eliminate also C1 from equation 1 and equation 2. Okay, so let's say we want to eliminate C1 first. So eliminate C1 from, so my light is flickering. So eliminate C1 from equations 3 and 1. Okay, so sorry about that. So my light is flickering. So now I'm using my camera flash instead. So I think I need to buy a new light. So again, we will eliminate C1 from equations 3 and equation 1. Okay, so to eliminate C1, so we will observe the coefficient, the terms that contain the coefficient C1. So as we can see, we have here a coefficient of 1, and here we have a coefficient of negative 2. Okay, so therefore, we need to eliminate C1, we need to multiply equation 3 by 2. Okay, so to make this 2 C1 here, and then we will add equations 3 and 1. Okay, so multiply equation 3. You will multiply it by 2, okay, and then add equation 1. Okay, so multiplying equation 3 by 2, so we will have multiply all the terms in equation 1 by 2. So this will become 2y plus 2 is equal to 2c1 e to the negative 2x, okay, and then plus 2c2 e to the 3x. Okay, and then add equation 1. So equation 1 is this, so no need to multiply it with anything. So plus, we have equation 1 is y prime is equal to is equal to negative 2c1 e to the negative 2x, okay, plus 3c2 e to the power of 3x. Okay, so adding those two, so 2y plus y prime, so that will become 2y plus y prime is equal to, so add this, so negative 2c1 e to the negative 2x plus negative, 2c1 e to the negative 2x plus negative 2c1 e to the negative 2x, so it will cancel out, so it will become 0, okay, and then adding this, so this will become 2 plus 3, so we will have 5 c2 e to the 3x. Okay, so let's name that equation 4. Okay, and then we will eliminate again c using equation 1 and equation 2. Yes, equation 1 and equation 2. Or we can also eliminate c1 from equation 3 and equation 2. Okay, so it actually depends to you, as long as we eliminate the same arbitrary constant using using another combination of the three equations. Okay, so we can use equation 1 and equation 2, or we can use equation 3 and equation 2. So I want to eliminate it using equation 1 and equation 2. So eliminate c1 from equations 1 and 2. Okay, so equation 1, equation 2. So as you can see, again, we will look at the term containing the coefficient that containing the arbitrary constant that we want to eliminate. So we have here negative 2, and then we have here 4. So we can eliminate c1 by multiplying equation 1 with 2 and then adding it with equation 2. Okay, so multiply equation 1 by 2. So equation 1 multiplied by 2, and then add equation 2. Okay, so multiplying equation 1 by 2, so we will multiply all these by 2. So this will become 2y minus 4c1 e to the negative 2x plus 6. Okay, c2 e to the 3x. So we will have 2y prime, okay, 2y prime minus 4 is equal to negative 4 c1 e to the negative 2x, and then 3 times 2, so that is 6, so plus 6 e as 6 c1 e to the power of 3x. Okay, and then we will add equation 2. So just copying equation 2, so we have y double prime is equal to 4c1 e to the negative 2x, and then plus 9 c1 e to the power of 3x. Okay, so adding, so 2y prime plus y double prime, so we will have 2y prime plus y double prime is equal to, this will cancel out, and then 6 plus 9, so we will have 15 this is c2. Okay, sorry, so 15 c2 e to the power of 3x. Okay, so let's name this equation 5. Okay, so from there, so using equation 4 and equation 5, we can now also eliminate C2. Okay, so eliminate C2 from equation 4 and 5. From equation 4 and 5. So how do we do that? So as we can see, we have equation 4 is 5C2, and then equation 5 is 15C2. Okay, sorry. So therefore, we need to multiply equation 4 by 3. Okay, and then subtract it by equation 5. Okay, so but by doing so, later on we will have a negative y double prime. So as much as possible, we want to keep the highest order derivative as positive. So we can reverse it. So we will subtract instead equation 4 from equation 5. So equation 5, this will become equation 5 minus equation 4 times 3. Okay, so rewriting equation 5. So equation 5 is this one. So 2y prime plus y double prime is equal to 15c2 e to the power of 3x, okay, minus equation 4 times 3. So equation 4 again is this. So multiplying each term by 3. So this will become 2y will become 3y. Okay. Oh, sorry. 3 times it will become 6y. I'm sorry, that is 6 plus 3y prime. Okay, so is equal to 15. Okay, so 3 times 5, 15 c2 e to the power of 3x. Okay, so subtracting that, so we have y double prime plus 2y prime minus 3y double prime minus 6y is equal to 0. So this will become y double prime plus 2y prime minus 3y prime minus 6y is equal to 0. Okay, so therefore, simplifying, our answer therefore is y double prime minus y prime minus 6y is equal to 0. So this is now the differential equation. Okay, so this is now the differential equation whose general solution is this. Okay, so it's basically just differential calculus and algebra. Okay, the elimination. Okay, so let's have another example. Okay, so for our next example, eliminate b and alpha from the relation x is equal to b cosine of omega t plus alpha, in which omega is a parameter and not to be eliminated. Okay, so solution. Again, if you don't know what to do, so let us think first that since we want to eliminate the arbitrary constants, then we count the number of arbitrary constants to be eliminated. It is said from the problem that we need to eliminate b and alpha. Okay, so we have to eliminate two arbitrary constants, so therefore we have to derive it twice. Okay, so solution from x is equal to b cosine of omega t plus alpha. Okay, so we will need x prime, or the dx over d omega. So you can just use x prime. Okay, so derive with respect to omega. Derive with respect to t. Okay, so t here is our variable. Omega and alpha are constants. So x prime, or you can use dx over dt. Okay, so we have b is a constant, so write that there. And then derivative of cosine is negative sine. And then copy omega times t plus alpha. And then chain rule, multiply it by the derivative of the function inside the trigonometric function. So the derivative of omega t plus alpha with respect to t is, what will remain is omega times 1 plus 0. So omega. So x prime therefore is equal to negative b omega sine omega times t plus alpha. Okay, so next we need the second derivative. So let this be our equation 2. Okay, this is equation 1. Okay, so x double prime is equal to, derive this again, so negative b omega are constants, so write them, multiplied by the derivative of sine omega t plus alpha with respect to t. So derivative of sine, that is cosine, and then copy omega t plus alpha. Okay, multiplied by chain rule, the same with what we did here. So the derivative of the function inside the trigonometric function cosine. So derivative of omega t plus alpha with respect to t is omega times 1 plus 0. So what will remain is omega. So this is, we need to simplify it first. So x double prime is equal to negative b, this is omega squared and then cosine of omega t plus alpha. Okay, so I think this can be solved using substitution. Okay, so as we can see, the trigonometric function cosine is recurring. Okay, so if we separate b, or if we separate omega squared, so this will become x double prime is equal to negative omega squared times b cosine of omega t plus alpha, right? And this from equation 1 is equal to x, right? So b cosine omega t plus alpha is equal to x. Okay, so therefore x double prime minus is equal to negative omega squared x. Okay, or we can say that x double prime minus omega squared x is equal to 0. Okay, so it's that simple because it's still it's just a recurring function. Okay, but the first example was more difficult, I think, because we needed to use elimination. So in this problem, we only used substitution. Okay, so that's all basically for elimination of arbitrary constants. So again, what you need to do is you count the number of arbitrary constants that should be eliminated, and based on that, you derive the function. Okay, based on the number of times that you have to eliminate the arbitrary constants, and from there, so work with your basic algebra to obtain the to obtain the differential equation, okay, without the arbitrary constants. Okay, so that's all. Good luck.